Welcome to all of you. Now we discuss about MCQ paper CC-7 semester 3 mathematics honors 2019. Question paper 2019. Question 1a. Suppose 1x, x square, x cube are four linearly independent solutions of a fourth order linear differential equation. If W be the Wronskian of the function 1x, x square, x cube, then which one of the following is true? Let y1 equal to 1, y2 equal to x, y3 equal to x square, y4 equal to x cube. Then Wronskian W for these four functions y1, y2, y3, y4, y1 dash, y2 dash, y3 dash, y4 dash, y1 double dash, y2 double dash, y3 double dash, y4 double dash, y1 triple dash, y2 triple dash, y3 triple dash, y3 triple dash. This determinant of size 4, order 4. So value of Wronskian after expanding, this is the upper triangular diagonal upper triangular matrix determinant of this upper triangular matrix. So the product of the diagonal principal diagonal elements are the value of the determinant. So this is equal to 12. The determinant of an upper triangle or lower triangular matrix is the product of the principal diagonal elements. So this is 12. So correct option is 4. So correct option is 4. Question B. If phi1, phi2 are two solutions of d2 by dx square plus ax dy dx plus bxy equal to cx, a, b, c are continuous functions on the semi-open interval 0 to infinity, then which of the following is a solution of the corresponding homogeneous equation? Phi1 and phi2 are solutions of the given equation y double dash plus ay dash plus by equal to c. Then phi1 double dash plus a phi1 dash plus b phi1 equal to c, and phi2 double dash plus a phi2 dash plus b phi2 equal to c. So because phi1 and phi2 are solutions of the given equation. Let z equal to phi1 minus phi2. Now z double dash plus az dash plus bz equal to, so this z double dash, so phi1 double dash minus phi2 double dash, a phi1 dash minus phi2 dash plus b phi1 minus phi2. So phi1 double dash plus a phi1 dash plus b phi1 bracket close minus bracket phi2 double dash plus a phi2 dash plus b phi2. This equal to c and this equal to c from the equations 2 and 3 respectively. So this equal to 0. Hence z, that is phi1 minus phi2 is a solution of the given differential equation. So phi1 minus phi2 is a solution. So correct option is 3. Next question C. The differential equation in bracket 3 a square x square plus by, this plus by cos x dx plus bracket 2 sin x minus 4ay cube bracket close dy equal to 0 is exact for what values of a and b. Here this is an exact differential equation, so comparing with mdx plus ndy equal to 0, m equal to this factor and n equal to this factor. So this del m del y equal to del n del x holds. Hence del m del y equal to this b cos x and del n del x equals to 2 sin x. So del m del y equal to del n del x gives b cos x equal to 2 cos x. So b equal to 2 and a is arbitrary. So b equal to 2, so b is 3, b is 4, b is 5. So only in option 1, b is 2. So correct option is 1. D. Question D. Let f x y alpha x square equal to alpha x square plus xy plus beta y square for alpha not equal to 0, beta not equal to 0, for alpha beta not equal to 1, then the sufficient condition for the local maxima at 0, 0 is what? Here the given function is fxy is alpha x square plus xy plus beta y square. So we find del f del x, del f del y, del f del 2f del x square, del 2f del y square, and del 2f del x y. So these are all partial derivatives for this. Now for stationary points, we know that fx at the point 0, 0 equal to 0, fy at the point 0, 0 equal to 0. So obviously 0, 0, because these fx these two alpha x y and 2 x plus 2 is beta y, obviously 0, 0 is a solution stationary point of this fx equal to 0 and fy equal to 0. So 0, 0 is a stationary point. Now for local maximum at 0, 0, if fxx less than 0 and fxx into fyy minus fxy square greater than 0 at this. So fxx means twice alpha, this is obviously less than 0, so alpha is less than 0, and this 2 alpha into 2 beta minus 1 greater than 0, because fxx is 2 alpha, fyy is 2 beta, and fxy 1, so alpha beta greater than 1 by 4. So alpha is less than 0 and alpha beta is greater than 4. Alpha is less than 0 and alpha beta is greater than 4, and obviously alpha is less than 0, hence alpha is less than 0, so obviously alpha beta greater than 1 by 4, so beta obviously less than 0, so correct option is 2. Next question E. Let y1 x equal to 1 plus x and y2 x equal to e to the power x be two solutions of d2y dx square plus p dy dx plus qy equal to 0. Then the set of and initial conditions for which a given differential equation has no solution is this. Here the general solution of this equation, obviously y equal to c1 y1x plus c2 y2x. Here y1 is 1 plus x and y2 is equal to the power x, where c1 c2 are arbitrary constants. Now differentiating 1 with respect to x, we get y dash equal to c1 plus c2 e to the power x. And for initial condition, first initial condition, this y0 equal to 3, y dash 0 equal to 1. So we get from 1 and 2, 3 equal to c1 plus c2, and from 2, 1 equal to c1 plus c2. So obviously c1 plus c2 is 1 and c1 c2 plus equal to 3 not simultaneously occur. So obviously the system is inconsistent, so we cannot find the values of c1 c2. Hence the given differential has no solution for this case. No solution for this case 1, first case. F. An integrating factor of the differential equation dy dx equal to 2x square plus y whole divided by x minus 2y cube is what? Here the given differential equation can be written as this: 2xy square plus y bracket dx plus bracket 2y cube minus x bracket dy. So comparing with this equation with dm dx plus n dy, so m equal to 2xy square plus y and n equal to 2y cube minus x. So del m del y equal to this and del n del y equal to this. So obviously del m del y not equal to del n del x. So equation 1 is not exact equation. Yet x to the power alpha and y to the power beta be an integrating factor of the differential equation. So multiplying 1 by x to the power alpha y to the power beta. So we get this equation 2. And then m equal to this factor and n equal to this factor. So obviously del m by del y equal to this and del n by del y equal to this. And since this equation 2 is exact, so obviously del m by del y equal to del n by del x. And then comparing the like parts of x and y. So here in the del m by del y x to the power alpha plus 1 beta x to y to the power beta plus 1, but in the right hand side there is no term x to the power alpha plus 1 y to the power beta plus 1. Obviously beta plus 2 equal to 0. And this term x to the power alpha y to the power beta in the left hand side, and right hand side is this minus alpha plus 1. So obviously equating the like parts of x to the power alpha y to the power beta from both sides, we get this beta plus 1 equal to minus bracket alpha plus 1. And so, and obviously this term x to the power alpha y to the power beta plus 3 in the right hand side, but there is no term like x to the power alpha y to the power beta plus 3, so 2 alpha equals to 0. So we get beta equal to minus 2, alpha equal to 0, and alpha plus beta equal to minus 2. So x to the power alpha, y to the power beta. So x to the power alpha, alpha means 0. So x to the power 0 is 1. And y to the power beta, beta is minus 2. So obviously 1 by y square is an integrating factor of this equation. And you can easily check this multiplying by 1 by y square and this m and n. And then we can find del m del y and del n del x equal to minus 1 by y square. And hence this is exact. So correct option is 1 by y square is the integrating factor of this differential equation. Of correct option is 2. 1 by y square. G, the general solution of the differential equation with constant coefficient d2y dx square plus b dy dx plus cy equal to 0 approaches to 0 as x tends to infinity, and if 1, 2, 3, 4 options. Here the given differential equation is y double dash plus by dash plus cy equal to 0, and the trial solution y equal to e to the power mx. So auxiliary equation is m square plus bm plus c equal to 0. So obviously m by Schubert's formula minus b plus b naught to the power b square minus 4c by 2. Let discriminant d equal to b square minus 4c is greater than 0. If this, then there are two real roots m1 and m2. Say m1 equal to minus b minus root over d and by 2 whole divided by 2, m2 equal to minus b plus root over d by whole divided by 2. Then the general solution of the equation 1 is y equal to c1 e to the power m1x plus c2 e to the power m2x, where c1 and c2 are arbitrary constants. Now, if y approaches to 0 as x tends to infinity, so obviously m is negative and m1 is negative and m2 is negative, because e to the power minus infinity tends to 0. So obviously m1 means this minus b minus root d by 2 less than 0, and minus b plus root d by 2 less than 0. So obviously b plus root d greater than 0, and b is greater than root d from this. Hence b is less than root d, and b is greater than minus root d. B is greater than root d, and b is greater than minus root d. So hence obviously b square is greater than d, that is equal to b square minus 4 is b square minus 4c. So obviously b square cancel, so 0 is greater than minus 4c, so c is greater than 0. So we get this b is greater than 0 and c is greater than 0. If d equal to 0, discriminant 0, then m1 m2 obviously minus b by 2, and obviously the equation reduces to c1 plus c2x e to the power mx. So e to the power mx, that means this b is positive. If b is positive, and then this tends to infinity. The solution tends to infinity. So obviously b is positive, and c is equal to b square by 4. So obviously c is greater than 0. So in the case of real roots, b and c are both positive. And if the complex root d is negative, then m1 m2 is equal to alpha plus minus I beta. That is alpha equal to minus b by a, and beta equal to root over b square minus 4c by 2 whole divided by 2. And general solution is this e to the power alpha x and bracket c1 cos beta x plus c2 sin beta x. Since cos beta x and sin beta x modulus value of both of these cos and sin is less than equal to 1, so this tends to 0 as x tends to infinity. If e to the power alpha is negative, this tends to 0 when alpha is x tends to infinity. So alpha is negative, then e to the power minus infinity tends to 0, then y tends to 0. So this, and alpha is negative means beta is positive. So b is positive because alpha equal to minus b by 2. So b is positive. So we get the relation b is positive. B is positive here. So correct option is both b and c are positive. Option 3. Question H, for xy belongs to R2, let fxy this x by mod x root over of x square plus y square if x not equal to 0 and this function 0 if x equal to 0, then del f del x at the point 0 0 plus del f del y at the point 0 0 equal to what? Question H. Now the limit h tends to 0, f of h comma 0 minus f0 0 divided by h. So if h comma 0, that means y equal to 0. So put x equal to h. So put this x equal to h, y equal to 0. So we get h into root over of h square plus 0 square divided by mod h into h whole divided by h, this h. And since h tends to 0, h not equal to 0, so we cancel this factor h from numerator and denominator. So this root over of h square by mod h. So root over of h square means mod h by mod h. So obviously this is equal to 1. So this is equal to del f by del x at the point 0 0. Now limit k tends to 0, f0 k minus f0 0 divided k. Now this limit k tends to 0, 0 minus 0 by k, because the function f is 0 if x equal to 0. So when x equal to 0, this function is 0. So 0 minus 0, that is by divided by k not equal to 0, k is approaching to 0. So this is equal to 0. So this the limit equal to del f del x at the point 0 0. So del f del x at the point 0 0 plus del f del y at the point 0 0 equal to 1 plus 0, that is equal to 1. So correct option is 3. Next question I. Let f maps from R squared to R be defined by fxy equal to bracket 1 plus xy whole square y not equal to 0, and f is 0 when y equal to 0. If the directional derivative of f at 0 0 exists along the direction cos alpha I cap plus sin alpha j cap, where sin alpha not equal to 0, then the value of cot alpha is what? Now, the definition of directional derivative of f in the direction of alpha, this limit exists. If the limit exists, del f by del alpha equal to limit rho tends to 0, f of a plus rho cos alpha, comma b plus rho sin alpha minus f of ab divided by rho, if this limit exists. Here, this P point AB and this point Q, A plus H, B plus K. So this is H and this is K and this alpha. And this distance is PQ is rho. So rho is root over of H square plus K square, and H equal to rho cos alpha, K equal to rho sin alpha, and rho tends to 0 as Q tends to P. The directional cosines of PQ is L, this is equal to cos alpha, and M equal to sin alpha. Here in this question, AB equal to 0 0. So P is 0 0 origin. So this limit rho tends to 0, f of 0 plus rho cos alpha, comma 0 plus rho sin alpha minus f0 0 whole divided by rho. So this equals to rho cos alpha, rho f of rho cos alpha, rho sin alpha. So the definition of this 1 plus rho cos alpha by rho sin alpha. So put this rho cos alpha by rho sin alpha, rho tends to 0, not equal to 0. So cancel rho from numerator and denominator, this whole square, the 1 plus cot whole square divided by rho. Now, if cot alpha equal to minus 1, this 1 minus 1, this 0, then the limit is in 0 by 0 form, and then this limit exists. So, for this directional derivative exists when cot alpha equal to minus 1. This correct option is 1. Next question J. A function fxy 3x square y plus 4y cube minus 3x square minus 12y square plus 1 has saddle point at what? This function fxy equal to this, so we can find fx, fy, fxx, fyy, fxy, the partial derivatives of this function fy. Now for extremum of the function f, we know fx equal to 0 and equal to fy. So fx equal to 0, 6xy minus 6x equal to 0, and 3x square plus 12y square minus 24y equal to 0. So x into bracket y minus 1 equal to 0, and x square plus 4y square minus 8y equal to 0. So from this first equation, either x equal to 0 or y equal to 1. If we put x equal to 0, then from the second equation, we get y equal to 0 or y equal to 2. So we have two stationary points here, 0 0 and 0 2. If we put y equal to 1 in the second equation, then from second equation we get either x equal to 2 or minus 2. So we get 2 1 and minus 2 1. So there are four stationary points 0, 0, 0, 2, 2, 1 and minus 2, 1. Now this h equals to fxx into fyy minus fxy square. So put the values of fxx. This is 6 into y minus y 1, fyy 24y minus 1 minus 6x whole square. So to 144 bracket y minus 1 whole square minus 36x square. Now h 0, 0 is 108, is positive. h 02 is 144, is also positive. h21 is minus 144, is negative, and h minus 21 is negative. Since f has saddle point at AB, if fxx into fyy minus fxy square is negative at the point AB, where fxab equal to 0 equal to fyab. So we have two saddle points here, 2, 1 and minus 2, 1. Hence here the correct option is minus 2, 1 because 2, 1 is not given there. So correct option is 4, minus 2, 1. And note that for these stationary points, obviously fxab equal to 0 and fyab equal to 0, and let h equal to fxx into fyy minus fxy square. F has local minimum at AB if HAB greater than 0 and fxxab less than 0. F has local minimum at AB if HAB is greater than 0 and fxxab is greater than 0. F has saddle point AB if HAB is less than 0. No conclusion if HAB equal to 0. This is the saddle point. This is surface, curved surface. This is the saddle point. If we approach along this curve, so this is the maximum point. This point is maximum. If we approach along this curve, this point is minimum. So this point is saddle point for this surface. Thank you for watching this video.